Okay, well, last day I tried to describe how this lab was going to work. I'm going to re-describe it again, though, just because some of the kids in Lundberg weren't here yesterday for it to hear, so it's probably worth doing a second time. Our goal is going to be to try to find the K spring constant based on the data we use when I use the simulator here for hanging springs, masses off of springs. Okay. One of the reasons why I have to use the simulator here is I don't have the apparatus to do this properly. One of the biggest issues I'm going to come across is that I need a frictionless spring. And I don't have a frictionless spring. The best I have right now is an elastic hanging from the roof. And that's not fantastic. I tried testing it out. Even when I try to hang a mass off of it and have it like fluctuate up and down, the mass usually just pops right off the elastic. So I don't have the apparatus, so we're going to try using this instead. My goal is for you to sketch two different graphs. One of your graphs is going to plot FG over X. And the slope of that graph should be the spring constant. Another graph we're going to plot is going to be pi squared mass over period squared. And the slope of that graph should also be the spring constant. And so what we're hoping for today, so long as things work out well, is in your analysis, just going to kind of sketch one out real quick. If you were to plot FG over X, I think it was, hopefully you'll get 4 points that make an exact linear relationship, and you can calculate the slope using, rise over run, and the slope, I'll call it M for slope, is supposed to be your spring constant. That make sense? If it works well. And then in your second graph, oops. Okay, what was it for this one here? Remember the what pi squared mass? And then it was period squared, I believe. And again, the same thing should happen. We're going to try to plot 4 points and hopefully get a nice linear relationship. Yeah, I hear something too. Like, I hear it from like right here though. Oh, over there. Alright, whatever. Move on. Does that make sense so far then? Okay. Here's one of the issues I'm going to have with the lab. In order to do this lab properly, I'd really like to have 4 points at least to make a graph. And one of the issues with my simulator, here's my simulator here, is that although there are different masses, this particular simulator has two different 100 gram masses. It has a 50 and a 250, and it has 3 unknown masses. And I think part of the lab that you could be asked to solve for is find the mass of these unknown masses. So I'd like to actually start with that. We won't actually put this in the lab, but in order to have a 4th mass, I'm going to try to figure out the mass of like this yellow one here, because it looks like it's kind of in between the 100 and the 250 grams. Does that make sense? It's just, it's not labeled. Correct. That's what we're going to do. Oh, sorry, we can't actually hang them on top of each other apparently, because otherwise I would try to hang them like together. Apparently I can't. This isn't actually that hard to fix though. Both of spring 1 and 2 actually have the exact same spring constant, and I know that because when I hang a 100 gram mass off of both of them, they both go the same distance. Does that make sense? So essentially what I know is that for spring 1 and for spring 2, their K constants must be the same as each other. I don't know what those K constants are, but I know they're the same. Does that make sense so far? Well, a simple calculation here then would say that for spring 1, spring 2, the K constants are equal to each other. What else is K supposed to be equal to though? Well, K is supposed to be equal to FG divided by X. Does that make sense? Their K constants are supposed to be equal to each other. Therefore, their FG divided by X's should be equal to each other. Well, how do we calculate FG? It'll be mass times gravity divided by X. It'll be mass times gravity divided by X. Okay. We're going to hang a known mass on spring number 1 and calculate how far it moves. we're going to hang an unknown mass on spring number 2 and calculate how far it moves, and that can tell us how heavy the mass is that we don't know what it is. Does that logic make sense? I'll do it for you. This is kind of a complex calculation. So I'm going to hang a 100 gram mass and calculate how far it moves. So can you guys tell on the scale how many centimeters this thing has moved? 10? Yeah, I'd say 10. This, like if I don't hang the spring on it, the bottom of this line right here to now that it's down here is basically at 10 centimeters. So I would say 100 grams yields 10 centimeters. So for the mass we know, this would be 0.100 kilograms. Gravity is 981, and it moved 10 centimeters? So 0.10 meters. Okay. On the other side over here, we don't know what this mass is going to be. So we're going to leave mass separate. We know it's going to times by 981, which honestly is kind of pointless. And I'm going to figure out how much the gold mass actually pulls the spring down. So then this gold mass is going to pull the spring down a different amount. And so I'm just going to measure and see how much that is. So that would be 10, 11, 12, 13, 14, 15 and half maybe? That makes sense? So then this would be 0.155 meters. So how do I get mass by itself then? You're just going to multiply out the bottom, because to be honest, the gravity that was on both of these equations, gravity was irrelevant in this particular solve, because gravity was the same for both. So I need someone with the calculator to give me a hand. Can someone take 0.100 kilograms, multiply by the 0.155 meters, and then divide by the 0.10 meters? 0.155? Okay, that makes sense actually, because really this one was a 10, that one was 100, so that should be the same there. Okay, so that means that this mass, the gold mass, must be 155 kilograms. That makes sense what I did there? So from the top, just to review, I don't need you to put this in your lab, just so you know. But the spring 1 and the spring 2 should have had the same k constant. Therefore, if k is equal to fg over x and fg over x should be equal to each other. Fg in both cases is equal to mg, but gravity was the same on both. So really what I had to compare was the mass of the 100 grams over how far it moved, and the mass of the gold one over how far it moved. And what I essentially found is how heavy the gold mass is. So now when we're doing our lab, if I can go back up to your results. In your results, you're going to have 4 masses. Mass 1 is going to be 50 grams. Mass 2 is going to be 100 grams. Mass 3, which is the gold one, will be 155 grams. And mass 4 is going to be 250 grams. And so those are the 4 masses we're going to use. But whenever I use mass 3, just know that this one is the gold one that's not labeled. Does that make sense? We're going to do a couple of different measurements. One of the measurements we're going to need to figure out is the x for each mass. And the other thing we're going to need to figure out is the period for each mass. Those are the two measurements we're going to take. And actually, that's it. Those are the only measurements we need. Sorry, go ahead, Sean. We should be able to find the spring constant. Let me go up here and show why. Sorry, I just lost all that. In this particular one right here, Fg over x, Fg is going to be mass times gravity, and then x is going to be how far the spring moves. So really all we need to know to solve this particular slope is the mass compared to the distance moved. Whereas this one right here is going to be the mass compared to the period. So we actually are only going to record 3 values: a mass, a distance that the spring moves, and a period for all three. And those are the only numbers we need. So please make sure you organize that in a table somehow, neat and organized. One thing I'm noticing as I'm marking some labs, please make sure that you include units everywhere and that you include proper labels. So if you're talking about M, please label it as mass in kilograms. If you're talking about T, please label it as period in seconds. Does that make sense? Please make sure you label all this properly. Whoa. Huh. How about this one? Okay, let's try the lab then. Okay, so I'm going to use the third spring, and the reason I'm going to use the third spring is because it's the only spring that actually has a variable soft or hardness, and I've set the spring so that it's going to be on this particular setting. So I don't want to move it off of this setting, because you guys might notice that as I make the spring like harder, I guess, it's making it a little bit thicker, and as I make it thinner, it's softer. So I believe I want to put it on this setting here, and we're going to try to figure out what its spring constant is based on this guy. So I'm going to start with 50 gram mass. Oops. So, oh my goodness. So first measurement we want to do is figure out how far the 50 gram mass pulled down on the spring. This is 10 right here, and I would argue that it's just before 10. So why don't we go 9.5? 9.5 centimeters. Okay. Then the 100 gram mass. Yeah, I'd probably go with 19.0. It looks like it's right on the line, give or take. So let's go with 19.0 centimeters. We'll go to the nearest, we'll go to the nearest tenth of a centimeter. So that's for the 100 gram mass. Oops. Then the 155 gram mass. Okay, I think this one's the 30. That's 31. 30.5 or 31.0? What do you guys think? 30.5. 30.5? Yeah. Okay, 30.5 we'll go with. And then the 250 gram mass. Well, I mean, it's way heavier. It should pull the spring down a lot further, right? So, okay, that's 40, 41, 42, 43, 44, 45, 46, 47. That guy right there is 48. You guys like 47.5? Okay, go 47.5 then. Okay. Okay, we're done half our lab in terms of the measurements we need. So one of our graphs then is going to plot the force of gravity. So take mass, which is either the 50, 100, 155, or 250 times by gravity. That's going to go on your y-axis, and the distance traveled goes on the x-axis. This should make a nice linear graph, and the linear graph should have a slope of your k constant. Okay, well that's going to be for the second graph. So now I'm going to redo all of this again. Only what I'm going to do after these guys are hung on the scale here is we're going to try to calculate the period of these things. So this guy is 50 grams right now. Okay. Now a couple of things I got to do when I do the period. I need to now make this a frictionless spring. So I'm going to take the friction and go from lots down to none. Because watch what happens when I leave it on lots. If I try to have this guy oscillate back and forth, it kind of stops right away, and that's not helpful. So I'm going to make it a frictionless spring. And so when I pull this guy down and up, he should go like so. Now I don't actually care how far he travels or even how fast he travels. All I require is the period, which is how long it's going to take this thing to go from, like, say, the bottom up to the top and back down again in that sort of wave pattern. For those of you guys in my grade 12 math class, that's basically the amplitude. Remember that term from yesterday, because that's from like the top down and up again. So. To make this work a little better, I'm going to go down to 1/16th time, and I'm going to throw a stopwatch on. So, Okay, so I'll start the stopwatch when it's at the bottom, and then we'll count it again when it gets to the top. Or sorry, not when it gets to the top, when it gets back to the bottom again. Okay, so that would be 0.6 seconds. I'm going to do this a couple of times though, just to make sure that I get the same value. Just because this is a little subjective. Ah, that was a little soon. I think it would have been 0.6 there, so I think I'm probably pretty close there. You might ask the question then, does it matter how far you pull the spring up and down? For example, I only pulled the spring down like a little ways. What happens if you were to like really like give this thing a lot? Would that make a difference? Well, let's test it. Because that's what ends up happening actually, is because it's going a further distance, it's going to go faster. So hopefully this ends up being 0.6 anyways. Does that make sense? I'm going to do it one more time here just to prove it. I'm going to do like the extreme the other way. So I'm hardly even going to pull this thing up or down at all. I'm just going to give it just a little bit of oscillating like that. Only I should turn the friction back off. So hardly anything. And then we'll slow it back down. This could be very slow. Does that make sense? So the actual speed at which this thing is traveling is irrelevant because the further away you pull it, the more speed you're giving the mass. So therefore the speed will make it up and it'll go the same distance either way. So long story short, let's go with 0.61. Wow. Let's go with 0.61 or 0.60 seconds for the period of the first one. We don't really need the ruler anymore. We can put that over there. All right, let's take off the friction, and we'll give this guy a pretty decent up and down. Okay, so I got 0.85 of a second, but let me try it one more time just to make sure that I wasn't way off. Ah, I missed it. Shoot. I'll try it from the top down, back up to the top again. Oh, I got the same thing twice. Okay, so go with 0.85 seconds for the period of the 100 gram mass. Okay, so this is the 155 gram mass. I can't actually see how far it gets down to the bottom, so I'll measure from top back up till top again. So from the top of a wave all the way down, back up till the top again.
Which you said was the amplitude?
Which, well, it's actually going to be double the amplitude. Technically, the amplitude is like half of it.
Oh, okay, from like the half.
So let's go with 1.10, and I'll just do one more try of that just to make sure I'm not way off. So 1.1 seconds. Technically, in terms of the waves we talked about yesterday, an amplitude, if you go up and down and back up, it's from like the midline up to the top.
Okay.
So like we need to find where like the middle point is, and then up and down should be equal though. Okay, so I'll try it there, the lowest point. Technically, we should be able to find that time there and double it. It should be hopefully the same thing, like from top to bottom. Same thing? Okay. Okay, and then we'll do one last one. We'll do the 250 gram one.
Yeah, it's huge.
Yeah. Okay, so friction is off. 1/16th time. I'm actually just going to let this one just drop. This thing should probably go for a decent ways.
Oh.
So I'm going to have to measure from top back up to top again. Eventually. It's a good thing we can do this whole 1/16th time, right? Otherwise, it'd be really hard to measure because it would be going pretty fast. Way down there. Let's go 136. We can take my word for that. Okay, that's all you need. That's it. So again, internet labs are a little bit different because we don't really get the same hands-on kind of work. But the trade-off is that the graph, unlike that graph that you guys did with the Hot Wheels car going down the hallway there with the weights on it, and the graph didn't work at all. This one should be completely linear, so long as things are going well. So, you guys have an hour. I'm thinking you should be able to finish most of the lab, if not all of it. So call me over if you need help, but that's all the data you need.
Can you go over what we're supposed to do on each graph?
Should I do that one more time then?
Yeah.
Okay, so now we have some data. Let me grab the lab here. On one of these ones, you're going to need to plot FG versus X. Okay, and the slope, here's the reason why. Let's just prove why again. The net force in like when the thing is held there is really based on like there's no movement whatsoever. So based on that, you can say that the force of gravity should be equal to the force of the spring. Okay. And then gravity is going to be mg, the spring is going to be kx. So if you divide by x on both sides, you would get k. And so that's why we're going to plot mg versus x. Okay. So you're going to need to make a table of values where you're going to need to plot the x value and the mass times the gravity. So give me the first one. How far did the first spring move again?
0.950 meters.
Okay, because you're converting it already, right? Yeah. So 0.0950 meters. And then how heavy was that guy? It was 100 grams. So that would be, it would be like 0.100 times 9.81. So that's going to be, can't do basic math, 0.981. And that'll be newtons. So then you're going to have to make a grid, and calculate it out for both axes. But like this right here might be where 0.981 newtons ends up being, give or take. And this might be where 0.0950 meters ends up being. And you're going to plot a point there. And you do the same thing for the next one. The distance then for the next one, let's just do one more. What was the next distance for the second trial?
19 centimeters.
19, so that'll be 0.190.
So the first one is supposed to be 50 grams.
Oh, thank you, 50 grams. Okay, so then that's going to be like half of that. So that'll be whatever that is, 0.4 something. Does this make sense to what I'm suggesting, Sam? I'm sorry I'm screwing this up. But then you should be able to plot another one, and it hopefully should be a straight line. when you plot all 4 of these, find me the slope using rise over run. And that should be your k value. And then to confirm that k value, we're going to do a second one. And then the second graph is going to be not based on fg, but it's going to be based on rearranging the other formula. Let me just reprove that one more time. The formula, the other formula is t equals 2 pi. Is it m over k?
Yes.
Okay, m over k. Okay, so then to get k by itself, we divided by 2 pi. We squared both sides, which ends up with t squared over 4 pi squared equals m over k. And then to get k by itself, we brought k up top. So k went up here. And then it meant that t squared had to come down to the bottom. And 4 pi squared went up here. Thanks, Heather. No, I'm just teaching. You know, education happening here. Hey, what's up? Okay. Yeah, I sent a few emails to people about that months ago. It never happened yet, so thank you. Okay. You're the person. Okay. Any other questions?
What is like the
For this one here? Okay, so then for this one here, you're going to want to plot a table of values where your, let's see, rise over run. So your rise is going to have to be, this will have to be t squared. This will have to be m times 4 pi squared. So then your mass was like, say, 0.050 kilograms times by 4 pi squared. You have to find what that number is. And then t squared, what was our first one? 0.6 seconds?
yeah.
So then you have to go 0.6 squared, whatever that is. Okay. And then plot one of them on the x-axis, one on the y-axis. And again, you should get hopefully a nice linear graph. Does that make sense? It'll be seconds squared. Yeah, you're going to have seconds squared, and then mass is going to be kilograms. Okay. Okay. I'll stop the video there then.